Hello, class. Welcome to the second online uh, lecture. I mean, lab. It should be lab as well, right? Um, the topic is, as you can see here, it is melting point. Again, because we are at the early stage of the semester, I'm telling you that you should have your pre-lab report written for melting point. So anyway, the melting point sounds simple. Yes, it is a simple technique. You prepare sample in a small capillary tube and you raise temperature at the proper rate and you observe the melting phenomenon and then you record it, the beginning and end of the melting. You get the range and you're done. But you're not just doing the technique, right? You are learning the theories behind. This melting point is touching solid and liquid, two of the most common states of matters. So it is very important for chemists to grasp the details of each states. Last two experiments taught you the kinetics and potential energies of liquid, right? In the distillation, how the kinetics from the heating is promoting the liquid to vapor, and how the dynamics of the vapor is causing the purification through the condensations and then re-evaporations. And also in the recrystallization, you learned things about solid, how the solid becomes stable, taking enough time to find the best stackings for the lowest lattice energy. We already have touched upon solid, liquid, and gas, and let's use that and intensify our understandings about um, the three states. Let's have a gentle video about simple procedure of melting, focused just the procedure. Then we will get into a little more about theories. So as I play this video, uh, you can play the video on your computer if you don't want to listen to this record for some reason, such as the audio is not good enough or something, right? So please do so. I'm in the office at work, and I don't want to be too loud. So let's see if this volume is good enough for you. If not, please, okay, play your own video. You can pause this video and play this YouTube video, okay?
Hi, welcome back to Educator. Today we're going to be talking about taking a melting point, which is a great way to analyze a solid. You might be using it to identify an unknown solid. You might be using it to confirm the purity of a solid that you've isolated and purified. And melting point obviously is a physical property of a solid compound, and the more pure the solid is, the sharper the melting point is going to be. And so that's why it makes it a great tool to not only tell us whether or not the compound matches the literature value, so that helps with the identification of the compound, but how pure your particular sample is by how narrow the range is of the melting point. So in order to prepare a melting point tube, we need to think about the different kind of tubes we have. In this one jar I have what are called capillary tubes. Capillary tubes are very narrow tubes that are open on both ends, and so we could use these to make TLC spotters or to draw liquids up, but these aren't melting point tubes. Melting point tubes.
There's a one minor concern, so I have to stop, like I always do, right? haven't done TLC yet, so you may not like get what she just said about TLC. Later, we do a technique called TLC, thin layer chromatography. You put one drop of your liquid sample on the paper-looking special device. It's not device, it's a paper-looking thing, and you put it on and you put it in a jar with a little bit of liquid, and you want to see separations of the one drop of liquid um, into whatever number of mixtures you may have as a spot, different spots on the TLC plates. So she says you can use this capillary of melting point for it, but no matter how small melting point capillary you get, that's not a good idea. Okay? Never use any type of a melting point capillary for TLC. We have a micro pipette, small, really tiny tube for TLC. If you blow that up, it may look like the one she's holding, but ours is really small for TLC.
Are capillary tubes that are sealed on one end. So they look like itty bitty test tubes, where they're open on one end and sealed at the other. And what we want to do is we want to load the melting point tube so that our sample is, our solid sample is packed tightly at the bottom, at the closed end, at a height of 1 to 3 millimeters. So if you don't know what 1 to 3 millimeters looks like, you should get a ruler and you should hold it up and you should measure it. And
Okay, if you have done your pre-lab, you know that sample size is important for the reason of heat conduction. With the beginners and amateurs, right, I found that 3 milliliter is a little too much unless you are really expert. So, since you are doing this first time, I would suggest to do it with as little as possible, even less than 1 millimeter. You know, it has to do with the control of heat that you apply until you get really clear idea and grasp of controlling the rate of heating. I suggest you to use a very small amount until you learn and feel good about it. Okay? Use a very small amount.
once you know what a couple millimeters looks like, then in the future you can go off your judgment. But go ahead and measure it first to figure that out. And so what we need, let's say on this watch glass I had my solid that I just done a recrystallization. I've just purified my compound, or I've isolated a solid, or I have one that I need to analyze. I want to get some of that into my melting point tube. The first thing I have to do is I have to make sure that this is a powder. If it's not already a powder, a lot of times it's they're crystalline. We might have some nice crystals there. What we want to do is kind of grind that crystal up into a powder. So take a small portion of your sample, a representative portion, and grind it up until it's a fine powder, because it's that fine powder we need to take the melting point. And then what we're going to do is we're going to scoop up just a little tiny bit of that powder into the top, the open end of the test tube of the melting point tube.
Okay, scooping. It's not always easy to scoop up because, as you can see, the opening of the capillary is extremely small. So what you do is you actually poke it. You hold it upside down like she described, and then you push it down through the pile of the solid. But we aim to have a little bit of it inside, so don't push it all the way down. Push it down like 1 millimeter and pull out and see how much you have in the capillary. If you need a little more, you think, then push it again just a bit. If it's enough, then you flip up the opening with a sample upward. Then you do what she's telling you. Let's see what she has to say.
And then we could just tap it on the counter to
that's really dangerous for beginner. Again, she's expert, that's why she can do that. But if you don't have a accurate vertical angle, as you tap it, you may break it. It's, remember, thin capillary. As you break, it is very sharp, needle kind of thing. And it's a glass. It could, yeah, puncture your finger, and some portion of the glasses can remain inside of your finger. It could cause a serious, injury. Depends on how hard you are tapping. So please don't tap. We have tubes that you can drop the thing through, okay, about a feet or so. From that height, with the guidance of the tube, that little capillary will drop gently vertically to the table, and that speed of the dropping will pack the solid. If you think that's not enough, you can drop a few times and repeat until you feel okay with the packing stage. Okay?
To get the solid to move from the open end all the way down to the closed end. Now, if you've jammed a lot of it up into the top and it's so packed up here, it's never going to move down. And so you should throw this out in the glass waste and just get a new one and try. So you want to scoop up just the tiniest bit, tap it down to the bottom, watch it move. And if you're tapping it directly on the end, it's quite strong and it can withstand that tapping. Or watch it to the end and then take a look. If you're not at a couple millimeters, scoop up a little more, tap, 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 move it down until finally you have a sample size at the bottom that's between 1 and 3 millimeters, and that's packed tightly. So we don't want air pockets in there, because then that's going to not give us even heating as we heat our sample. So we want it nice and tightly packed until and at the proper height. And again, if it's less than a millimeter, you can't really see the sample very well to make your analysis. If it's more than 3 millimeters, again, you're going to have a problem with uneven heating, and so you're not going to get an accurate measurement there. So that's why it needs to be both tightly packed and somewhere around a couple, just a couple millimeters.
So that's for the expert. For you guys, have, like I said, less than 1 millimeter. Trust me, with my 50-something-year-old eye, I can see. Okay, you can see it. Don't worry. And more than that, at your skill level, you will have a trouble with the heat, evenly heating samples.
Now what I have here is an example of a melting point apparatus, and it's got a couple things. It's got a heating block, so it's going to heat our sample. I slide this in. It's got a little slot to hold the melting point tube, so I put the closed end down with the sample in it, and it's got a heating block that the sample is now resting next to. It's got a thermometer to tell me what temperature the unit is at. And when I hit the power switch, it also turns on a light, and it has a little magnifying glass, so I can look in this window and I can see my sample. It's going to be magnified, so I can see these crystals very clearly. It also has a dial here to control how quickly I'm heating the sample. So this controls the rate of the temperature of heating, and you only want to be you don't want to be heating it too quickly, because if you're heating it too quickly, you're going to have a heat lag between what the melting point apparatus temperature is and what the crystals really are. If it's heating too fast, then you're going to have a lag, and your crystals aren't really going to be as hot as the thermometer is. So you need time. As it rises slowly, it equilibrates as it rises, and you're going to get a much more accurate thing there. Another problem with it heating too quickly, not only the heat lag, but also you're going to, when you observe the melting, you have to step up and read the temperature. And if by the time you look up here, the temperature's already changed, you again aren't able to record an accurate temperature. So you want to heat it slowly. If you know the range of your melting point, approximately where it's going to melt, you can maybe heat it a little faster to get close to it, and then more slowly. So, or you can, and if you have no idea what your sample is, you can even do a quick melting point that's fast heating to get a ballpark range of where it's going to be. And then
okay, so she's giving out a lot of information, so I have to pause to give you a chance to organize your thought, what you heard from her. First part was explaining the machine. Second part, when you do measurement, things that you need to be aware. Okay. Um, One thing I want to make sure you understand, and she kind of said it wrong. This bottom box of the unit is not heating unit. Okay, this is where the electricity and the voltage is modulated. It's controlled to generate the different amount of heating rate, like she said, heating rate. So setting the dial at certain number doesn't determine the final temperature. Temperature's gonna rise continuously. The difference is different rate, how quickly the temperature is rising. That's what this is all about. Okay? The setting is not determining the final temperature. Like we normally would think with our experience in the kitchen, right? This is about heating rate. Then the electricity and voltage is controlled and it is flowing into the heating unit that's up here, protected up here. Why we have this metal shield is because we put our eyeball where the magnifying glass is underneath of this window. There's a separate little magnifier, small circular tube thingy, and that is connected to the chamber where you have a three small slots. You can barely put three tubes of the capillary. She put one, but there are three slots there, side by side, nearly touching. Overall dimension is like about 1 inch wide for three sample, and then maybe 2 inches depth. Bottom of the tube is where the magnifying glass is attached to, so you can examine the melting phenomenon, but it is a closed system. It's not open. And then the whole thing is made of a metal because it's going to be heated. So heating is taking place right here. It's closed chamber with a three entrance. Okay? And right next to, right behind, you don't see it, but right behind on the same metal block, the thermometer is touching. So the heat that's generated by the electricity you control with this thing and the coils down here, it's not going to be heated down here, okay? The heat is going to be applied to the sample and the thermometer. Given heat is the same kilocalorie, but thermometer is different thickness compared to your capillary. So heat conduction, you can imagine, from the metal heating block to the sample tube and versus to the thermometer are different. So you have to always be cautious that the thermometer of the tube where the solid feel the heat is not necessarily same as temperature you read from the thermometer. That's why this heating rate control is extremely crucial, and that's why I say beginners until you learn how these things work properly. You don't want to have enough sample in your tube. Okay? So she's going over connecting the anatomy of the machine and little background of the units, how it works, and connecting that to the melting experiment.
And you can take a more careful approach with the second melting point to get a more accurate one. Okay, so anyway, this dial is going to tell you the reason there's a dial. Sometimes you do want to take a fast melting point, but most of the time you want it to be slower. And so we're going to be watching our crystals, and there's two things we're going to be watching for. There's two temperatures we're going to be recording, so we're going to make sure we always have a pen in hand and our notebook here, so we're ready to record the data as we're taking it. We don't take little scraps of paper towel or something, and then transfer it later. This is your data. You need to record it live. So I'm going to be watching as it's heating up. I'm going to be watching the crystals, and what I'm going to look for is the first sign of melting, and this is when your crystals start to look wet, for a significant amount of wetness. Now, you might notice that the crystals kind of shrink a little bit. That's called sintering, and that is not melting. So we ignore that. But so it doesn't matter if they're moving a little bit, but you want to see when it starts to look wet. That is melting, and so we're going to record that temperature. That's the first temperature of our melting point range. And then we're going to continue watching our crystals, and bit by bit, you're going to see the rest of the bulk of the crystals are melting. And then finally, you're going to see the very last crystal disappear. And now what you see in your little mini test tube is just a liquid, total 100% liquid, no crystals. That's your final temperature. So you take a quick look up at your thermometer and record that temperature. So that's going to be your melting point range, the point of first melting and the point of the last crystal disappearing. And that's what you're going to report in your laboratory notebook. And you always record a range. When we say take a melting point, we mean take a melting point range. So there always needs to be two numbers. Even if it appears to just melt instantaneously, you could write the same number twice, and so you have a 0 degree range or maybe a half a degree range. That's okay. And the indication of purity is a pure solid is going to have a sharp melting point. So we expect that range to be just 1 or 2 degrees, hopefully. But when we have impurities being introduced, organic impurities, that breaks up the crystal structure, makes it a lot easier for it to melt, and so it will melt at a lower temperature than the literature value typically, and it's also going to melt at a wider range. So that's going to be our evidence that we have not as pure of a crystal. So
yes, so she gives out very core concept of the melting, which is equivalent to stability of the lattice energy. We partially got some idea from the recrystallization experiment, but it's too brief and not clear enough. So we will take time to go over that concept, and our exam questions will be heavily on those deep theories. So you should pay attention to the chemistry behind. But yeah, of course, you need to know the conclusion, like pure sample will have a narrower, which she referred to sharp, but narrower range, beginning and the ending of the melting within 1 or 2 degrees, sometimes 0.5 degrees, something like that. But impure ones can have more than that. Even it could be 15 degrees apart. So yeah, we'll see why that is the case for impure sample. That's how we figure whether the sample you created is pure or impure. And there are other methods like the TLCs and other methods to figure out the purity even more sophisticated manner. But melting point is a quick test for the purity as well, not just the measuring melting point. Also, melting point is a quick test for identification if this is one of the known sample. But for unknown sample, you can't because you don't know the melting point. One thing you have to be always careful is there are so many compounds that has very similar melting point. So melting point alone is a never good way of really confirming the identity, the name of compound. Okay? It never is. You should rely on spectroscopy, other more sophisticated tools. But like I said, it can be quick tests for the known samples, especially when you use mixed method. She did not go over that, but hopefully the other video does go over the mixed method, teaching you the quick test for the what compound is this unknown, if the unknown is actually known to you.
Melting point is a really great diagnostic tool, and it's anytime you're isolating a solid product, it's most definitely one of the physical properties you want to record to characterize your product. So good luck with your melting points.
Thank you, ma'am. Nice lecture, and thank you for the good teaching. Um, Before I start lecturing, let's listen to the video too today. Oh, the MIT.
Throughout your laboratory experiences, you will frequently need to assess the purity or identity of a crystalline solid. Both of these goals can be accomplished by determining a compound's melting point. When a compound is in a crystalline solid state, the intermolecular forces that are holding the molecules together greatly outweigh the kinetic energy that is trying to pull them apart.
See the approach, kinetic energy, and the lattice energy. Right? The kinetic energy is the heat we give. Currently, the lattice energy, which is a potential energy, also which is the attractiveness of each other due to the polarities and charges and structures and all those factors, right? Happen to be stable enough at the room temperature amount of the kinetic energy. Doesn't mean they will stay like that forever. We start giving heat energy, we give them more and more kinetic energy. It will be accumulated into every single molecules. The balls are not atoms, right? Balls are symbolizing certain shapes of molecules in the lattice of solid. It's gonna move and move vigorously and eventually start moving away from each other and turning into a liquid.
Therefore, the molecules appear to vibrate in a fixed location. If energy is introduced into the system in the form of heat, the kinetic energy of the molecules, and thus the temperature of the system, is increased. At a certain point, the molecular kinetic energy is high enough to overcome the attractive forces that are holding the molecules together. As a result, the crystal lattice breaks down and the molecules enter a liquid state. The temperature at which the solid and liquid phases of a compound are in equilibrium at a certain pressure is called the melting point. In reality, a solid melts over a temperature range instead of at a specific temperature. Because this range is a physical characteristic, it is reproducible for a pure compound. For example, N-phenylacetamide melts between 114.2 and 114.9 degrees.
See, 0.7. This is done by professionals. But when you're doing with a excellent skill, the numbers are reproducible. But if you guys are doing first time, though it will get better and better, right? It could be 3 degrees apart at first, and don't feel like you are not good enough, because most of the first timers are getting 2 or 3 degrees ranges easily.
Celsius. Therefore, the term melting point really implies a melting range. Although a variety of melting point apparatuses are commercially available, this video will demonstrate the determination of melting point by using the MELTEMP.
Here we go. This is the inside of the blue casket you saw earlier, right? There was a window, remember? And it was protected here. So inside, this is the window I was mentioning, and it is connected to the chamber inside. The heating is done by this core, the cylinder metal piece. And then here you have thermometer inserted to this tube, and these are one body. And this capillary is going into this chamber area where it is observed, right, through this window. and you have a two more slots, and this width is about 1 inch or less, and the height is about 2 inches or less. And this is light bulb. You have a little opening behind around this height, behind this tube, facing this end toward the sample. It's going to light up inside of the chamber, so we can see the dark chamber. Okay, so this was protected. But if it's not protected, you know where you should not touch, especially with the face. This whole thing. Okay, this window here is a little better. It's warm, but yet you never know. If you raise the temperature too high, then this can get a little hot. Okay. If you ever see the unit, melt temp unit without cover, be careful. This is heating unit. That's why I had to correct. This is not heating unit. This is a heating unit, so you can be safe in the lab. I told you first day, safety for you is more important than learning. Yes.
The melt temp apparatus consists of an on-off switch, a sample holder, a light source that illuminates the sample, an eyepiece that magnifies the sample, a digital thermometer which indicates the temperature of the system, and
unfortunately, we are not using this. Lately, we got some unit. Not sure we're gonna have this for every person, but we do have some. But before the COVID, we did not have many units with this digital recorder. But this one is connected to the digital thermometer, inserted to this slot instead of the glass thermometer. So make sure if you ever have a unit attached to this, the sensor is actually inserted to. Otherwise, this is not reading the actual temperature, but it's going to read the room temperature.
the voltage control. The voltage control dictates the rate of heating with a higher setting corresponding to a faster rate. The voltage control does not control the temperature of the system. Use caution when touching the melt temp and always assume that the apparatus is hot, especially the part that is labeled caution, unit hot.
Okay, take a moment and imagine this in your head. Okay, the Organic 2 class will require you to know how to operate this, but we're not doing this experiment, so I have to make sure you know how you do this experiment. Orgo 2 professor will not teach you this. They will start judging you. So through this, you see sample. The light is off, so it's dark. But you'll see 1, 2, 3, bottom portion of the tube that you inserted and magnified, obviously. And then light will go through this tube into the chamber behind this, which is around here, right? This portion, this chamber. It's the perspective from the top. This one's hot, but also this part is hot. This eyepiece part is not as hot, but this part behind is hot.
Part that is labeled caution, unit hot. The first step in determining a melting point is the preparation of the crystalline solid. To prepare the sample, you will need a spatula, a watch glass, a mortar and pestle, capillary tubes that are sealed at one end, and a long piece of glass tubing, such as a long stem funnel. Before proceeding, ensure that the crystalline solid is clean and dry. If the solid is wet, you can try to pat it dry with filter paper. Do not place the sample in the oven, where it may melt or decompose. If your sample consists of large crystals, you must first crush them into smaller crystals with a mortar and pestle. Large crystals cannot pack together well, which creates air pockets. If air pockets are present in your sample, then a time lag for heat transfer will exist, causing the crystals to heat unevenly. If you do not have a mortar and pestle, you can use the flat end of the spatula to grind the sample instead. After crushing the crystals, place them on a watch glass. Turn the capillary tube upside down and thrust the open end over the crystals. A small amount of crystals should be trapped inside the capillary.
Yep, you see, they don't scoop up, right? We poke it down.
Invert the tube to its correct orientation and pack the crystals down to the bottom by gently stroking the tube or by tapping it on your bench top. If the
Nice, they're using funnel as a dropping tube, but we have a dropping tube at York.
crystals fail to fall to the bottom of the capillary, then drop the capillary through a length of glass tubing. A long stem funnel works well for this application. You may have to repeat this action several times to ensure that the crystals are effectively packed down. Loose material.
Yeah, so that's not well packed. This is like a hypothesized situation. You're not going to have something like that. But even when you look at the area, it looks almost packed nicely, right? There's so much air bubbles. You know why the paddings are warm in the winter? Because it has lots of air bubbles, and air means no heat transfer, right? Solids, liquids are transferring heat better. So feathers with a lot of air bubbles and empty spaces between the feather material keep us warm. So when we heat this up, heat is not going to transfer through the solid all the way to the up. Okay? The thermometer, I told you earlier, may not read the same temperature. Thermometers keep going up because it's made of solid and liquid. And heat is keep applied because we set it that way, and temperature keep rising. And the temperature already reached melting point. So the bottom is melting, but heat is not conducting upward well, so not everything's melted. Therefore, your beginning of melting is almost correct. But you have to wait until everything melts to get the second number of the range, right? Melting point is actually melting range, she said. But because it's not packed well, it's going to take a while. Meanwhile, the thermometer is saying like a higher and higher and higher temperature. Then eventually the top solid melts, and then you get that number, which is the incorrect number, much higher number. Okay, so your melting point will be elevated than the actual melting point it should have been because you didn't pack well. Also, imagine, even when you packed well, if you have so much sample, like a 3 millimeter rather than 1 millimeter, right? And you say happen to have little too fast heating rate. I said it's not temperature, right? It's a rate. So temperature rising quickly. And thermometer, no problem. It's catching up the speed, and temperatures keep rising on the thermometer. But this thing is not so dense. Even it is, it's melting the bottom part, but it takes time to go up. Even with a good packing, if you have a 3 millimeter, right? You have to wait until complete melt. But by the time it reach here, the temperature was already enough to melt, but it only takes time because you have so much sample. But thermometer don't wait because you put the weight a little higher than you're supposed to because no one knows, only you get the feeling from the practice in order to be expert. So the thermometer again read the higher temperature than it's supposed to be, and then you get the elevated wrong readings. So even with a good packing, too much samples not good enough. especially beginners, more is the worse. So I said, get less than 1 millimeter.
Material contains air pockets, which cause the sample to heat unevenly. Ideally, the smallest manageable amount of material should be used, which correlates to
Obviously, I'm teaching at the MIT level. That's my expectation, obviously. But look at them. They are not giving 1 millimeter. As much as you can manage, like you can see and you can detect, right? Smallest possible amount. It makes sense, right? Why 3 milliliter? They don't tell you. That's a memorization. It's not science.
amount of material should be used, which correlates to a depth of approximately 1 millimeter of packed material. If the depth exceeds 2 millimeters, inaccuracies may result due to uneven heating. Prepare 4 capillary tubes of your sample. One filled capillary tube will be used to determine a crude melting point, and the other 3 will be used to determine your actual melting point in triplicate. If you do not know the expected melting point of your compound, you must first determine a crude melting point. Finding the approximate melting point of the sample will save a lot of time when performing the actual measurement. To determine the crude melting point, set the voltage on the melt temp to 0 and wait until the apparatus has cooled to room temperature. Insert a sample, increase the temperature at a rate of 10 to 20 degrees Celsius per minute, and record a rough temperature when the sample melts. To determine the melting point of a crystalline solid, set the voltage on the melt temp to 0, turn on the power and the digital thermometer, and then insert a filled capillary tube into the sample holder. If the temperature is lower than 20 degrees Celsius below the expected melting point, then dial the voltage to a setting that enables the temperature to increase at a rate of 10 to 20 degrees Celsius per minute. After the temperature is within 20 degrees Celsius of the expected melting point, dial down the voltage so that the temperature increases at a rate of 1 to 2 degrees Celsius per minute.
Yeah, you can feel what's going on, right? Say you are riding a horse. When your destination is far, you really run fast. But when you reach the destination, you need to slow down to be like accurate and stop right where you need to stop, right? So when you give heat in the beginning, far from the melting, you got it from the crude melting, quick melting. Then that's not accurate melting temperature because you did it at the high speed. Thermometer shoots up, but your sample doesn't do that, right? I explained. So the temperature you read is like a little elevated. If it's melted at the crude melting attempt, 100 degrees Celsius to 102, right? For example, it's not going to be 100 or 102. It's not going to be higher. It will be most likely lower because you're reading, as I explained, at the elevated heating rate. For the quick, guess is exaggerated number. It's elevated number. So your melting will be like 90 whatever, or who knows, 80 whatever. Okay? So when you do actual melting, don't rush at the high rate up to aiming to like 100-ish. No, because that number is exaggerated number. You should aim for like slowing down around 70 something, 80 something. You slow down because you never know where it is exactly. So you slow down. Then you give heat really slow to find the exact melting. If you have enough time, obviously you can see now it's better from the beginning heating slowly. Then your heating speed for the solid, which is naturally slow heat conducting material of the sample, because you unavoidably have some air bubbles between solids you grounded, versus the thermometer that has no empty space. with a really excellent heat conduction. It's made to be excellent. Okay. At low speed, they will have a same progress. Okay, so if you have a sufficient time, do it slow anyway. Just like if you can manage, use minimum amount possible.
Per minute. Watch the sample through the eyepiece and record the temperature when the first
See the
crystal
melting
starts to melt.
phenomenon? You see, it's not really melting, right? You can see different types of melting. Sometimes the solid collapse down instead of causing like liquid formation. Liquid is forming, but it's all over the place. It's with a solid, so you don't see liquid. It's just some portion of the solid disappear as a liquid, so solid is collapsing due to the gravity. Sometimes it appears to be like solid start to have holes here and there, punctures here and there, like a beehive, or sometimes the solid appear to evaporate and disappear. So there are all kinds of melting phenomena you need to get used to and learn to catch the beginning. It's very difficult to catch the beginning. End is easy. No matter what type of melting phenomenon you observe, if all the solid is disappear into whatever form, right? You know it's end. End is easy. Beginning, you may miss. Okay? You need to pay attention to the beginning part.
Melt, which means when the first droplet of liquid appears. Finally, record the temperature when the last crystal disappears. Turn down the voltage, remove the melted sample, and throw it into the proper waste receptacle. Allow the melt temp apparatus to cool to 20 degrees below the melting point of the compound, and repeat the process 2 more times with the remaining samples to ensure reproducibility. Never remelt a compound because it may have undergone a chemical change while heating, such as oxidation, decomposition, or rearrangement.
Therefore, you have some chemical reaction due to the heating. The new compound you created by oxidation, decomposition, or whatever is acting as impurity because it's different from the original compound. And remember, when you have an impure compound, right, due to the impurity you just created, the melting point will change. Okay? The statement by the first teacher in the first video, the pure compound will have a narrow melting. Impure compound will have a wide range, and even the initial melting can be significantly low by 10 degrees, 20 degrees lower than it's supposed to be, only because you have some impurity there. That little impurity, if you remember the recrystallization, the impurity can lower the efficiency and stability of lattice packing. So the solid becomes very unstable and it can easily break down with a little bit of kinetic motion energy. Therefore, you don't want to reuse melted sample again. Never say it looks okay. It looks to your eye okay, but our eye is not that precise. We are not doing kitchen lesson here, right? We are doing science. ppm, ppb, parts per million, parts per billion level of toxic chemical can kill people if you are working in the pharmaceutical industry. You are making a serious mistake if you ignore that type of thing.
The point where the first crystal starts to melt can seem ambiguous to someone taking a melting point for the first time. As stated earlier, this is the point where the first droplet of liquid forms. It is not when the material begins to settle, soften, or shrink. Only the appearance of a liquid droplet indicates the beginning of melting. One common use for melting point is to assess the purity of a known compound. If an impurity is present in a sample, it will interrupt the crystal lattice and weaken the forces of attraction that are holding the molecules together. Therefore, the sample will melt at a temperature that is lower than expected. The sample will also melt over a wide temperature range. As a general guideline, if a compound melts over a range greater than 2 to 3 degrees Celsius, it is most likely impure. Another common application of melting point is the identification of an unknown crystalline solid. To identify a solid, simply compare the melting point of the unknown with the melting points of known compounds that are listed in a reference book. Typically, just the upper limit is reported in these reference books. When combined with other spectroscopic data, you may be able to identify your compound. To confirm that your compound is indeed what you think, prepare 3 samples containing mixtures of your unknown compound and the proposed compound. 20 to 80, 50-50, and 80 to 20 are good ratios to start with. Determine the melting point of each mixture. If all the mixtures melt at the same temperature and within the same range, you may have correctly identified your compound. If they do not, then you definitely have not identified your compound. There are several ways to obtain inaccurate melting point readings. The most common mistake is increasing the temperature too rapidly. In this situation, the capillary will not have enough time to equilibrate with the heated block. As a result, the melting range will appear narrower than it actually is, and the melting temperature will appear higher. A sample that disappears upon heating indicates that it is subliming instead of melting. To remedy this problem, seal the open end of the filled capillary with a Bunsen burner before placing it in the sample holder. A sample that changes color upon heating is probably undergoing decomposition. Decomposition must be reported along with the melting point of the compound. If the melting point is still incorrect after troubleshooting, or if you need to confirm the accuracy of your result, you must calibrate the melt temp apparatus. To do this, find pure compounds with known but dissimilar melting points. This video will use naphthalene, N-phenylacetamide, salicylic acid, and succinic acid. Determine the melting point of each pure compound and compare the value you received with what is expected. Plot the actual melting point of each compound against its observed melting point. Use the resulting calibration curve to determine the expected melting point of your compound. Determining the correct melting point of a
Just a sec. Yeah, so this curve is not only calibrating the unit, but also thermometer, okay? So it is calibrating whole setup, including thermometer. That way, whatever you do experiment with the same setup, you read your temperature, say as a 150 here, and you extrapolate, and you can read exact temperature, like 150.2 or something. It is only reliable when you have a nice linear correlation. If your data points are not within like this, right, 99.99% on the line, then yeah, you have to do the calibration experiment again. Maybe your melting technique is not good enough.
Determining the correct melting point of a crystalline solid involves good technique in both sample preparation and in taking the melting point. To ensure accurate results, use a minimal amount of solid, pack the crystals tightly together, and increase the temperature slowly. Determining the melting point of a crystalline solid is the best way to assess its purity or establish its identity.
Thank you. Okay, so I want to take a break. for 10 minutes instead of stop recording and restarting. If I do that, we'll have two videos. I'm gonna pause. I'm gonna, yeah, stop microphone and then I'll come back in 10 minutes. Okay? See you later. All right, welcome back. Yeah, so the online classes I chose, such as this one, Melting Point, they're the relatively short and simple ones. The one that we actually do are the somewhat more important and more lengthier one. So I think we can finish this one a little earlier. Um, anyway, okay. So when you look at here, last time I showed you this, you need to be aware of these. Okay, the why is it not working? Okay. So the basic techniques and property measurement, and we just did melting point. All right. And also we talked about solubility during the recrystallization, but I said we need this technique here and there. So make sure you know how to do it. Um, we have done different types of filtration for the essential techniques, and we did distillation. We have done recrystallization, right? And we'll be doing extraction pretty soon. And then the midpoint of the semester, chromatography. We mentioned the TLC today, okay? And we also just heard about the word spectroscopy, and I believe you have seen UV spectrometry during the general chemistry laboratory with the heavy metal. And one of the definition given out by the MIT person, the melting point is the temperature when you convert solid to the liquid. Last time we did the boiling point, liquid to the gas, a certain point, right? That temperature. But we said the boiling point can change, depends on the pressure. So today, surely, she said the melting point as well at a given pressure, she said. Melting point is not constant, okay? It is a factor of a pressure, not only temperature. So if you change pressure, can change the melting point. That's why you can skate ice. On the ice, you stand on, okay, you have ice, you stand on with a sharp knife and you have a body weight, okay? So say I'm about 70 kilogram, and on the knife you have such a small area, right? Area is like length times width or something like that, right? So the knife is like what? 0.01 millimeter. I mean, it's smaller than that, right? So the area is really small. So 70 kilogram divided by small, whatever square meter, right? Whatever it is, it's gonna come up with a very high Pascal pressure. So we create so much pressure on the ice. When you pressurize it, what happened? Melting point change. That's why underneath the knife of the skate, this ice solid turn into liquid and acting as a lubricant. That's why you can slide. But when you pass it, some of the water you just created under the pressure will go back to solid. Okay? So this phase diagram is showing the relationships between those melting and boiling and sublimation points with the pressure and the temperature. We have a good awareness for the temperature role because it's kinetic, but people do forget very easily about pressure because we live in the very stable atmospheric planet. Also, another phase diagram is this. We talked about how the boiling curve should be, right? Ideal boiling curve or the simple boiling curve or fractional boiling curve. So somebody asked me like, how do we make the curve? We didn't do experiment. I said, if you listen to my lecture, I gave more than twice a hint how to come up with the curve based on the theory. Theory for the simple, theory for the fractional, and the ideal ones if you know what samples you choose to. And then I said, if you have, say, a liquid, whatever the real name, okay, you choose to be, say, boiling point was 100, and the other one you chose was a boiling point 150, and you gotta have a boiling point for A and the B. But when you mix at different ratio, what happened to the boiling point? In terms of boiling point, you get average of them, right? When you break pure A and the A, it takes 100-degree amount of the heat. When you have a mixture, you have a A and the B bound. So when you boil, you break the bond between A and the B, not A and the A. So this attraction between A and the B, while the B is more polar and attracting better, this force is greater than that of the A and the A, but weaker than B and the B. So it should be between somewhere around, right? 150 to 100. Depends on the ratio. That's how you imagine the curve. Simple distillation not able to separate A and the B, so you got a lot of the high boiling B mixed in, so boiling point of the mixtures are pretty high. But fractional distillation is gonna get rid of the B from the vapor mixture, so you may have a more pure A vapor, so the temperature will remain almost ideal. And then near the boiling point of the second one, after removing most of the A, it is going to jump to the next boiling point, 150 from 100. But again, most important lesson about the distillation was it wasn't the case you boil the mixture at 100 degree and you got the A. Then you boil the rest of them at 150 and you got the B. It wasn't the case, right? I said that in order to get A, you need to break this bond, so you don't boil at 100. It has to be much higher than 100. But even so, after boiling from the flask, it has to go up as they hit, they condense down. So you have to give them more temperature so they can travel high. Therefore, to evaporate 100 degree of vapor reaching the top of the fractional distillation, the flask may be at around 400 degree-ish Celsius temperature. So it's not like you set temperature at 100. That's really funny, I said. Okay, that's this situation. And we are looking at right here. Again, while you are giving heat, it's supposed to maintain temperature like ideal, but it doesn't. Remember, temperature that you read, not necessarily the temperature in the solid with a different amount of solid and also different degree of a packing and other factors, the rate of heat and stuff. The thermometer may read keep going up. Okay, unideal situation. If you have a more sample, this can be extended. Because it takes more heat to melt everything. Say yours is not ideal and you have 3 times more, then it keeps going up 3 times. Then the difference, the deviation is even worse, greater. So solid turning into the liquid sounds simple, but it has to be measured considering all other factors. The factors we didn't look into was impurity seriously, right? If you have impurity, the packing could have been really stable, but it doesn't. So what does a low melting point means? It means you give a gentle motion energy, which is a low heat, okay, less heat. This array of attractive solids around the impurity is easily breaking down, meaning turning into liquid. Without purity, you need a lot more serious shaking in order to break this down, the solid down to the liquid. Even when they have a same melting point, people may easily say, oh, the compound has a strong attractiveness as it does in other shape of compound. Maybe so, but you never know. However, say you mix them up, okay? Get rid of this thingy, one block of this molecule, and you put this molecule, presumably having about same amount of the attractiveness power. Put it there, a different shape. Then you can see easily, because of their charge distribution in different shape, the attractiveness for this square block by this hexagonal block is not effective. This block would have been attracting all around distributed charge for other neighboring blocks effectively. But this hexagonal may have, I don't know, but based on this melting point overall may have about same amount of attractiveness, but because the block shape doesn't allow them to have a maximum, look at here, look at there, look at there, look at there, those corners. They don't have a maximum attraction. No, not utilizing all these attractiveness from different shape of molecule. So when you explained the melting point, if you're only saying intermolecular interaction, as if stronger polar one should have a strong high melting point, is incorrect because you leave out one of the most important factors, the packing in the lattice. which comes mostly from their shape. Soon in organic reaction, an organic lecture, you're going to learn this cyclohexane is actually drawn this way, which is wrong. This is a real three-dimensional, but this thing can be existing this way as well. If you stack this up and stack that up, they should have a different melting point, though they are same cyclohexane compound. The shape determines. Why would they change the shape? It depends on the situations. That's what you're learning in the lecture. So I am giving you one leverage, okay? As you learn new concept, you have to remember, oh, Dr. Lee said shape is extremely important to predict the properties. We're not just learning different shapes, giving different energy. You're going to talk a lot about steric angle strains and 1,3 diaxial interaction energy and all kinds of energies associated with a different shape. But also this lattice energy, okay, that affects melting point, solubility, and everything. In our pharmaceutical department, we have Dr. Masumichi. His research is about crystalline, how crystal shape affect the potency of drug. Same drug, but the crystalline structure will give different effect. The same compound. So you'll explore eventually all those little bitty, for lay person, right? Common people will think, oh, that's not important. It's the same stuff, right? Yeah, it's the same stuff, but they have a different property. That's what the expert will say to them, and you are turning into one of the experts who can explain the details. So yeah, intermolecular force is important, but that's not all. Okay? Which one's more important? I would not say intermolecular force is more important. I would not say shape is more important. They're equally important. This is a new curve. You've seen this type of a distillation curve. Here you have a melting curve. This axis is the temperature. This axis ratio of the two mixture. Just like you have a two mixtures of a low boiling and high boiling liquid, when you have a different ratio, the overall boiling point changes. The more low boiling liquid you have, the mixture will have a lower overall boiling point. Like I said, right? The attractiveness to the B in the mixture is weaker by this guy, so breaking that to transform into the gas is easier. But as you have more and more B's, the overall boiling point increases. That's what I said. Raoult's law. And I am telling you the conclusion for melting point. In melting, this is the opposite. Okay? The Raoult's law only applies to the boiling. What's the Raoult's law again? More attractive high boiling compound ratio increases, then the overall mixture's boiling point increase. It makes sense because you have a more attractive guys. Then overall, they are more attracting one another. So opposite in melting point, you mean you have a more attractive guy and it's gonna have a lower melting point? Yes. Okay, yes. It's right here. Pure high melting, Q. Pure low melting, P. When you mix, right, When you mix any amount of the high melting or low melting, whatever you mix, it's a mixture, meaning one is main compound and the other act as impurity, meaning besides these two pure states, any other states, they are impure states. And look at the melting point. They are lower than this. They're lower than this. Whatever you mix, right? You had a low melting point and you start mixing 0.1% of the high melting, right? What happened to the melting point overall? It drops. It doesn't go up. It doesn't go up as you add more attractive B. Stronger intermolecular force Q, because it has a high melting, you may think, and it should be stronger. That means it needs more heat to melt. It should have been this way, but it's going opposite way. Okay? So, no matter what it is, if you have impurity, you just destroy the solid easily. Okay, with that said, let's understand this curve a little better. Say you have 80% high boiling, 20% low boiling, okay? 80% solid at room temperature. You start to heat up in the capillary inside of the chamber of the melt temp machine. You raise temperature, but sample is a sample, right? In the capillary. You ground them up well, and you don't have a much air bubbles. Say you pack them very nicely, and you have a under 1 millimeter. Very nice. I cannot mimic that, but you know what I'm trying to do, right? If you enlarge one of the particle, I enlarge the particle, okay? I told you last time here, whatever molecule you are talking about, you have 1,000, literally 1,000 of them. Last time I explained with the actual number. So when you heat up from the bottom metal heats up, the vibrational energy, because the solid has only motion of vibration, that vibration energy hit this solid grain, shaking all these molecules up, shaky, shaky, and it transfer upward and shaky, shaky, right? As the individual molecule shakes, all these carbons go shaky, shake, 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 right? All these hydrogens shaking, shaking. That vibration obviously collide into the upper away from heat source, bombard into, and it's gonna let go, shake, 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 warm up, and then it goes transfer to the carbon, shake, 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 warm up, warm up. I'm trying to give you molecular vision of ordinary phenomena. Okay, you're gonna now you're getting chemical eye allow you to see things that ordinary people don't see. You boil cattle for coffee at home, like I do every day. Now you imagine how these things boil and condense down. Okay, so heat transfer taking place, but until it reach here, the particular temperature here, it's not necessarily melting point of P or Q. It's much lower. Okay, that temperature. So what is that temperature? So significant. Dramatic things happening right there. So to understand that point, you go back to our earlier example. Yours is not pure. You have some impurity. And you are shaking this thing. Where does it melt first? Around the impurity, right? Around the impurity at the much lower motion energy, meaning at the much lower melting point temperature, it melts, not these pure area. If you imagine big array of these boxes, right, and you have these two of them, only this area will melt. The other area is just like a pure stuff. It's still strong. So you can see every single little dust particles you pack nicely has thousands of them, but some area will melt first. Okay, that is this point. So once you melt away the impurity, what's left is a pure stuff, right? So as you melt, say you had hundreds of boxes and you only have a two impurity, and the two of them melts with a couple other boxes. So as you melt these two impurities, say you melted 10 boxes out of 100. The 90 boxes are still there and they're all pure now. Because impurity, two of them, the 10, the main compound box, they're in the liquid. It's already melted at the low temperature, okay? So here, all those impurities and somewhat some portion of the in this case 80% was a Q, so Q melted, but there are some more remaining Qs, right? Depends on how much you originally had. So after melted them away, the melting point will jump up here because now you have only pure stuff left. Then the rest of them melts right there at this temperature, which is a slightly lower than the pure Q, because it's not the same anymore. Why? I said the remaining ones are pure, but you have a liquid. Remember, you have a water and a solid like sugar or salt. To melt, literally heat up and melt salt, it takes 1900 something degrees Celsius, nearly 1000 degrees Celsius of a heat energy. But if you have a liquid with it, what happens? You can destroy the crystal of salt at room temperature. You can dissolve salt at room temperature right into water. So presence of a liquid will obviously affect the temperature, but because the remaining ones are pure, the melting point, even after affection from the effect from the liquid presence, it will be close to the pure Q. So initial melting you observe around here. If you're expert, you catch it, but if you're not, maybe you're catching around here. That's the initial boiling, melting. Say that was a 130, okay? It could have been down here 128, but you caught it at 130. And then it melts here. It could have been 150, but you caught it at 148. Oh, no, sorry. The pure ones are 150, but it will be 148. And I told you the ending is easy to catch because that's when the last solid disappear. The beginning is difficult to catch, but you will most likely will catch the ending. That's why impure solid have a wide range. In this case, my example I just made up is 18 point degree, easily. Okay? It's not always when you have two different melting points. I told you earlier with this example, even when you have a same melting point solid, if they are different molecules, they have a different shapes and the charge distributions, then when you are mixing them, they will not melt at the as the same as if it's their same solid. They will give you wide range of melting because the weak array of the solid due to ineffective packing, okay, from those things that I mentioned before, will give this low eutectic point. So that's how you read this melting curve. Let's see. Yeah. Yeah. Yep. Yep. We got some of these digital thermometers, and we have some different units, completely different unit, much more advanced one than this one. We don't have enough devices, but when you are taking Orgo 2 in-person class, almost every lab you have to measure melting point. Okay, if you're asking the professor, "We didn't learn," you're lying, and can you teach me again? Then the person will remember you that you didn't know. So you better master it now. And the reason I'm mentioning different style is because they have a slightly different ways of operating. So whenever you get machine, you need to read. There will be always a little direction written on the machine. Besides the universal Meltem unit like this is a universal all over the world. Some other institution purchase different style, then they should have some instruction written out. So like the MIT person explained, we do make some mixed sample because we can have a similar melting point. Then we don't know which one's what. For example, we give you T-cinnamic acid and the urea, for example, and you're not going to measure this precisely like that, right? Whether you measure this or this, you are getting around the 132 to 136, okay, around this area. And only because, say, you got 131.9 to 133 versus 132.2 and 135. Oh, this one's closer to this, and that one's closer to that. So I'm gonna say this is my cinnamic acid, and this is my urea. Then I'm gonna say, do you really trust yourself to judge by what difference you have? 131.9 to 132.2, 0.3 degree. I mean, you think your measurement technique is that accurate? Instead, more reliable method is, say your unknown really is a T-cinnamic acid, okay? But you don't know. You only have a melting point close to this and this, and you don't know. Then you grab T-cinnamic acid or urea, one of them. Doesn't matter which one. Say you pick the urea and you mix them up. You don't know what this is though, okay? You mix them up and grind them up well, and then you measure melting point. Then what should happen? They are different stuff. So your melting point suddenly will be different, so much different from your two measurements. It's gonna be like a 122, 131 or something, right? So wide range and different. Then you know, oh, I just mixed the urea to my unknown. Therefore, my unknown is not urea. It should be tisonamic acid, the similar melting one. But if you are the type of person, oh, I want to ensure, okay? You know, I had uh, the lab mates having argument, loud yelling argument, because one person, I have to ensure I'm gonna have to do it, and the other person, dude, this is so obvious, you know, there are only two similar, and this is not it, then it must be this. But I have to actually see it, you know, but I have to go now, you know. So I said, stepping in, okay, stop fighting. You can go. You can do it. Problem solved. Anyway, so yeah, if you're the type of person you need to see, then you, instead of urea, you pick now tisonamic acid mixed with your unknown sample, and without knowing this is your tisonamic acid because it's unknown, right? And you grind them up and you melt. Because they are same thing, you will have one of these two, or similar, something like this with a narrow range. Then you know the unknown is the one that you just mix to have a same melting point, which is a tisonamic acid, right? That's why this concept of impurity will change melting point range dramatically. So I said, and the MIT person said, if the melting range, even at your skill level, first timer, okay, by the time when you take Orgo 2, you shouldn't be this level, but anyway, you get 2 or 3 degrees, you can still consider them as a pure, but if it's more than that, okay, then they're not pure, they are different. Then it should be safe. If you are extremely good at it, then you know you have a much better sense of judging your mixed method results. Yeah, this lab, even when we do actual lab, it's a somewhat shorter. And I cannot get the question from you, so it should be even shorter. I think that's it. What you have to do for post-lab is find melting curve for a polymer. Polymer is not like a small molecule, right? It's like a spaghetti. And you have a solid state of a polymer, which means you have wet spaghetti in a bowl and you let it cool down. Then some parts of spaghetti cling to the other string of a spaghetti, and the other portion cling to whatever you can imagine, right? So they are elastic, but they are solid, and breaking all those bonds with a several other string of spaghetti attached to each other of several of others is impossible. So the melting phenomenon is much different from the normal organic small compounds. So instead of me telling you how it's like, because you are college student, you need to know how to retrieve the informations. It's so easy these days. I used to go to a library and look up the books and journal papers. These days you can Google, you know. So Google, watch YouTube video, understand the melting phenomenon. Before melting, there's a special process. Okay, I'm not going to mention it. You need to differentiate those processes. How the melting point of the polymer is really different from the other temperature. That you need to clearly explain, like I explained with a molecule. Yeah, that's the only thing you have to do as a instead of data, because we don't have the data. Okay, instead of data processing, you do that. Okay, until then, have a great one. See ya.